All right, everyone. Welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington, and today I'm joined by Arash Behboodi. Arash is a machine learning researcher at Qualcomm Technologies. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Arash, welcome to the podcast.
Yeah, hi Sam. Thanks for having me.
It's great to have you on the show, and I'm looking forward to the chat. I'd love to have you start out by sharing a little bit about your background and what led you into the field of machine learning.
Well, my background is information theory and mathematical signal processing on the one hand. My PhD was about basically deriving Shannon theoretic bounds on information capacity of certain cooperative networks under channel uncertainty, so kind of mathematical PhD work. And after that, kind of transitioned into in the field of compressed sensing. It's quite fascinating to me because the core problem in compressed sensing was you have certain observations of an unknown signal, but you don't have enough observation to recover it fully. So you have to rely on some prior assumption about the signal. And the question is, if you know that prior, what is a good, how you can recover your signal, and what are theoretical bounds on basically sample complexity, how many observations you need, and all that. So kind of dealing with that notion of a structure, signal structure, and how this can be used in different kind of inverse problems, that was very, very interesting for me. And kind of I was working on that afterward. But then, of course, deep learning comes with a lot of interesting promises and challenges. So it's immediately I said, maybe with deep learning can even do better with do a better job of working with the structures and learning better recovery algorithms, and even from theoretical side, I was very interested in understanding like mysteries of deep learning. So I think kind of that dragged me into deep learning. But funny enough, on the side note, when I was undergrad, one of my main interests was philosophy, and kind of I did that in parallel during my whole life. And when I was doing my PhD in parallel, I also did a master degree on that, and kind of a lot of topics that I kind of studied there, philosophy of mind, language, and all that. Question of meaning, intelligence, consciousness, all that's kind of re-emerged in this field of machine learning again. And kind of it became a very exciting area to work on, and kind of I'm happy that all my interests are coming together within this field.
Oh, that's fantastic. Fantastic. What you're at obviously Qualcomm AI research now. What are your primary research interests on that team?
Yeah. So, I talked about information theory and compressed sensing and mathematical signal processing and wireless communication. Of course, Shannon theory is mathematical theory of communication. So kind of communication and wireless communication in particular has always been very also interesting to me. And I worked on that also as kind of a motivation for a lot of problems I was formulating. And so what we're trying to do here, we're basically looking at wireless communication from machine learning perspectives, put it that way. We're trying to understand how we can design new machine learning architectures useful for different wireless tasks, and how we can improve different parts of kind of wireless system design using machine learning. And this kind of relates to the current technologies that we have and the next technologies that are going to come. And so the research that we have, I like to call it wireless AI research. So it's a kind of doing machine learning research for wireless communication.
And one of the papers that we're going to talk about that you have had accepted at ICML this year is in the same field of compressed sensing that has come up a few times. Sounds like it's an area that you're continuing to explore pretty deeply.
Yeah, absolutely. I think, the inverse problems, they're everywhere. We kind of from medical imaging to all sorts of kind of, we can talk about drug discovery problems, protein unfolding is another example. So you can find a lot of areas where inverse problems are important, and wireless communication is actually full of those problems, like from channel estimation to other topics. So you can find a lot of inverse problems, and yeah, I mean, the compressed sensing is definitely like a core interest for me there.
Now, I've talked to some of your colleagues about some of the work that other teams are doing in compression. How does compression and the setting there compare with compressed sensing? Is it the same? Is it different?
It is different. So in compressed sensing, the idea is that you want to efficiently sense the environment in order to infer something. In compression, the idea is you have a source, you have an information source, and you want to efficiently compress it. So there is no sensing medium there. The only thing that's important is that how well you compress and reconstruct your information source. In compressed sensing, the idea is how you sense the medium given the constraint that is given to you. You do not choose that, and then how well you can reconstruct based on the observation you have. So they're conceptually they might be connected, but they're kind of a parallel field, I would say.
And so, with that said, what is the motivation for your ICML paper, which is called Equivalent Priors for Compressed Sensing with Unknown Orientation?
Great. So let me start, with first talking about generative priors and its relation to compressed sensing. I think this is probably a good start. So, what when I talked about the structure, so assuming some prior about the structure of the signal, for example, a typical example of a structure in classical compressed sensing was sparsity. You assume that your signal is sparse in a given basis, for example. And then you use that to some sort of L1 minimization to basically find your signal. Now, with deep learning, with generative models specifically, we notice that actually generative models provide a way of parameterizing a space of signals of interest using basically the latent space of the generative model. So, and specifically, if you cannot tractably represent a signal, in this case, let's say images, if you cannot tractably represent a prior, generative models provide a way of parameterizing that. And there was a work by Bora and co-authors around 2015 that showed actually you can use generative models, and you do gradient descent on the latent space of that generative model in order to estimate the signal. So generative models in that sense provide a structural prior on your signal. And the paper showed quite interesting results, and it was quite an encouraging work with theoretical guarantees on top, which is always good to have. So that was the original work. Now, a lot of work came afterward, basically using flows, using different techniques for doing a better job in this thing, or extending it into different type of nonlinear problems and various extensions. Some challenges that these models have are, let's say, convergence and latency, meaning that sometimes when you do gradient descent on the latent space, you might need to restart the whole process because it's not converging. So the convergence and the way you optimize your problem can become an issue, and especially if you're interested in low latency, let's say, solutions, that can become a bottleneck. So there were actually some works about how you can effectively invert a generative model, and actually Alex Dimakis from the TU Austin had some follow-up works. Actually, it was a co-author of the original paper. Some follow-up works on kind of a layer-by-layer inversion and some other tricks following that as well. So that's one part, like why generative models are relevant for compressed sensing. The other part was, okay, in many applications, we might not have, when we want to measure a signal, the signal might go under some transformation, let's say some rotation, before the measurement. This can happen. A typical example is a cryo-electron microscopy. So cryo-electron microscopy is a way of basically taking a picture of a biomolecule. You can look at it like that. And the problem is that when you take this picture, of course, the picture is very noisy and all that, but the molecule that you have is in an unknown orientation, right? And if you have multiple pictures, these orientations are not the same, so are not aligned. Also, you can find in different, so you can, in general, you can think of a signal that you actually can train a generative model on, but the orientation of that signal might change before the measurement. So you might say, okay, what I can do probably is I try to first figure out the orientation and then reconstruct the signal or doing it iteratively, basically solving the problem like that. What we thought was, why do we need to kind of separate orientation discovery and the signal recovery? So we can do this jointly. And the way we can do it is we can train a generative model that has already this information embedded in it. Of course, you can say, what we can do, we can get a generative model, use data augmentation, and basically now we have it already there somehow because we have seen all these different orientations. But when we know that we want to have this steerable, basically transformable latent space, equivariance models are excellent candidates. So what are equivariant models? So the equivariant models are models that when you transform the input of the network according to certain group transformations, let's say rotation. When you rotate the input, then the features that are output of that network also rotate. So therefore, a rotation, a change of orientation at the output correspond to the change of orientation as the input. This also imposes some sort of a structure on the latent space of your generative model. So the main idea was, let's try to use equivariant priors so that we can just solve this whole problem altogether.
Awesome. Now, I've talked with colleagues in the past of yours about equivariance as well. I think in the context of those previous conversations, we're primarily talking about supervised types of problems. Has equivariance been applied to generative types of problems previously?
Yeah, this is a good question. Actually, the answer is yes. The answer is in context of the generative model, there have been some works that try to incorporate this equivariance into the model architecture. The way we kind of did that in our work, the kind of equivariant VAE that we built, as far as we know, and as far as I know, this is the first time that we have such an equivariant VAE constructed. But at the end of the day, I think another example that comes to my mind is the kind of equivariant normalizing flows. That's something that has been published, I think, last year. So one challenge of those works are they're very nice and elegant, but kind of scaling them up to kind of a problem that wants to have low complexity, low latency, which is actually our main motivation at the end of the day. Scaling them or bringing them to to that type of problem, it becomes a bit challenging. For example, for equivariant normalizing flows, you had to work with this type of a kind of a continuous time neural networks, like ODE type models, and training those models are difficult. Scaling them up are difficult. And what we're targeting here is just having a nice small equivariant models that can perform already quite well compared to the counterparts.
How did you, assuming you started with a traditional VAE type of an architecture, how did you evolve it to be equivariant based, or to understand equivariance?
So equivariant, so variational autoencoders, you have an encoder network and decoder network, right? The decoder network is the network that's going to be used for our recovery task, because that is the generator part, and we were going to use the latent space. So we want the output orientation change. So basically, transformation of our signal translates into the transformation of our input. So what we want is that the generator of the network should be equivariant. So the decoder network will pick an equivariant network off the shelf from the existing models. Now, what happens to the encoder network? The encoder network basically in VAE gives parameters of your approximate posterior. So if we're assuming that we have a Gaussian type posterior, you have a mean value and you have a covariance matrix basically. Now, when you rotate the image, your encoder network is going to give you a distribution, basically approximate posterior. You will get a new distribution when the input is rotated. What should be this distribution? So consider random variable corresponding to the untransformed image, right? When you transform that image, you want to get a new random variable that is the transformed version of that. So basically, if the distribution that you want it to correspond to the transformed random variable. So okay, so that we know. Now, what happens to the parameters of this distribution? Let's just start with mean value. The mean value, as we wanted, is when we transform a random vector with a rotation matrix, for example, then the mean value of that random vector is also transformed according to a rotation matrix. So this basically means that the part of the network giving us mean value should be equivariant. So that is also figured out. The challenge is for the covariance matrix. When you transform your random vector according to a matrix, let's say A, you have A times your random vector. The covariance matrix changes according to A times the previous covariance matrix times A Hermitian. So we do not have like the classical equivariance anymore, because if you transform your input according to A, the covariance part should be transformed according to A Hermitian. First conclusion out of that is that we cannot use the typical diagonal covariance matrix assumption used in VAs. So we need to consider like a full covariance matrix. Another thing is how we're going to build this this transformation, this type of network. So the way we did that, we said, okay, covariance matrix is a positive definite matrix. So we can already write it down as a V transpose. I mean, we considered other ways of parameterizing that as well. So we write the covariance matrix, the positive definite covariance matrix as V transpose. And then if that V matrix is equivariant, so it's just transformed, then the whole covariance matrix satisfies the condition that we want. So we built the decoder network giving us the encoder network giving us the covariance matrix in a way that that part of the network is equivariant, and it just parameterizes basically the V presentation. There are other ways of doing that, but we tried that also in the paper. More or less, they give same performance, all of them.
And does the way that you approach that, does that apply constraints to your inputs?
There's no constraint necessary on the input. So the only thing you need to know is how the transformation that you're interested in, let's say rotation, acts on the input space. That's what you need to know in order to build your equivariant networks. You need to know how the input is transformed so that the equivariance is built into the architecture. That's the only thing you need to know. Otherwise, you don't need to put any constraint on the input.
And so how did you go about assessing the performance of the architecture?
So what we did is said, okay, of course, we are interested in recovering signals with unknown orientation, right? So we said, let's try to pick like a powerful flow networks with, the most powerful flow network normalizing flow network that we can have, like a typical real MVP setup. And then let's try to iteratively find the orientation and kind of a latent space, latent code by just a gradient descent on the latent. This is the so-called vanilla or like a baseline that we had. And then we compare that with our VAE, equivariant VAE method. We had other baselines as well, but I think the normalizing flow is the most interesting part because it usually gives the best result in terms of reconstruction. So we noticed that our equivariant VAE is much simpler, it's much smaller, and it already gives same or better result than flows in many cases, which is more complicated, and then you have to do all those iterative assumptions and all that. And then something interesting happened as well, that even if the orientation is known, so or you don't have any random orientation, actually equivariant VAEs turn out to perform quite well in this task. And our conjecture is that actually the equivariance adds certain additional structure on the latent space that makes the life of optimization algorithm much easier, and therefore we can do a lot with it. So that was an interesting thing. So the gain was not only in terms of reconstruction quality, not only in terms of finding unknown orientation, but also in terms of latency, convergence, which are kind of important metrics for these generative priors. I really think like latency and convergence are metrics that are quite important for applicability of these methods in practice, especially if we could target something that requires implementation on edge device, low latency constraint. That is quite crucial.
You talked about wireless and cryo-electron microscopy as the use cases. In the microscopy case, there's kind of this obvious image that you're trying to work with. In wireless, are we talking about applying this to images that happen to be transmitted wirelessly, or is there some um, application of the same idea to broader wireless problems?
That's an excellent question. Actually, so let's just start with uh, the new kind of frequency band that is being introduced in 5G. It's kind of a millimeter wave frequency bands. So when we go higher in frequency for wireless communication, what happens is that the beams become basically you need to use directional beams to get the performance that you want. These are some artifacts of like having a smaller antenna aperture and all that. So to summarize the whole thing is that you just cannot rely on kind of a rich scattering environment that you have in order to get signals that you want. You need to really be able to steer your beams, your antenna beams, in a direction that kind of gets the most energy, and also direct your beams and design your beams accordingly. Now, if you want to do that on your device, and kind of I leave it at a high level like that, if you want to do that on device, you're usually kind of keeping your device and you're talking, and then you put it on the table or walk around. Your device is permanently rotating, right? But the environment is the same environment. It's just the way you view it is changing. So it's kind of undergoes some transformation. So that is the main idea in wireless communication. So that's why kind of incorporating those geometric priors in our design, wireless design, becomes really crucial, especially when we talk about these high frequencies.
Speaking of wireless, what are some other research areas that you're pursuing in that domain?
I think look at wireless communication. At the end of the day, we are working with laws of physics there. You have Maxwell equations, and at the end of the day, there is an electromagnetic wave moving from one point to another, undergoing a lot of effects in an environment, reflected from different objects, scattered, diffracted, and all that. That's the underlying nature of wireless communication, is kind of physics, right? So modeling these uh, complicated propagation effects real precisely, it's a challenging task. And the way people traditionally build models, at least so far, so you have two class of models for wireless. One is a kind of a ray tracing type models, which is based on just kind of deterministically following paths of the ray. And you have what I can call a statistical channel models that kind of build an average case statistical model, that you put a distribution on the channel gains that you have, on the delays that you get, and you work with those hard-coded assumptions. Now, with machine learning, we know that with using data, we can build much better models if we can just use those models to build either better statistical channel models or better kind of more especially consistent channel models. So one of the research areas that are is quite important for us is exactly this channel modeling, which basically is about kind of learning physics. This is a kind of a topic. It's not limited to wireless. You know that there are other folks working on neural networks, physics inspired neural network, or neural networks that can learn physics. So that's a topic that is quite interesting. And one thing that we did was, let's try to gather very simple field data, not requiring really kind of hard, really like special devices, and let's build a generative model on that generates the underlying channel, sort of implicitly learns the underlying channel. So that's kind of one of the works we had, and we continue to work on those topics as well. The other thing that is quite interesting is wireless perception. So again, our visual perception is still based on electromagnetic waves. It's just a different frequency. Of course, it's much higher frequency than what we're working right now in wireless. But on the other hand, in wireless, we might have access to much more details, much more refined concepts than what we probably have visually. So the question of wireless perception and sensing is quite important as well. Like how we can build right now, let's say, machine learning models that can perceive the environment through the lens of wireless signal. And also, that was one of the topics that we were working on, basically trying to solve a simple SLAM problem by incorporating physics of propagation into the machine learning model and try to learn that from a wireless signal.
SLAM being the same kind of SLAM that comes up in robotics, simultaneous location and mapping, I think.
Precisely, yeah, some sensor localization mapping. So that's exactly the same thing. But this time you want to do it with wireless signal.
Awesome. Awesome. So, kind of returning to ICML, what are some other papers that you and your team or other teams at Qualcomm are presenting there?
Yeah, I mean, there are a couple of very interesting works from my colleagues at Qualcomm, and the first paper that I want to mention is a paper that has some kind of oral presentation paper this year at Qualcomm, and it is about basically oscillation of quantization-aware training. So basically, and dealing with those problems. So to give a little bit of background on that, again, you probably talked with some other colleagues before that they work on quantization and compression of neural networks. So
It's
we
come
know
up.
that, yeah. So we know that kind of with quantization, let's say with the post-training quantization techniques, you train a network, you go and quantize it, you can actually get very good performance, decent performance with 8-bit quantization out of these networks, right? So this is quite interesting. However, if you want to push this quantization down to 4 bits, then just post-training quantization techniques are not sufficient for pushing the performance. So you need to basically do what people call quantization-aware training. This basically means that the quantization noise that kind of is added because of quantization operation, you include that in the training process. So what you're doing is that you quantize and then you backprop through the quantization operation. Now,
So the network can learn to minimize those errors as it's training.
Exactly. Now, when you backprop through the quantization operation, basically the technique that's used is straight-through estimator, like one of the techniques. So the straight-through estimator, what it does is that you basically have your shadow weights, basically weights that they live in real valued numbers, and they get quantized by quantization operation and gives you your quantized value. And now, when you backprop at inference, you work only with quantized values. So that's the ultimate network. However, when you're training it and you backpropping through that, the straight through estimator is roughly speaking, means, okay, forget about the quantization operation that you have here, just directly backprop through the shadow weight. That was the real number. So that is the rough idea. Okay, that already helps kind of overcoming some of the difficulties. However, it is not sufficient. And one interesting phenomena that can happen is that when shadow weights are close to quantization threshold, so basically threshold between two different quantization beans, they start to actually oscillate around that. And if you look at the quantized value now, they oscillate between different quantization beans. And this oscillatory behavior has been reported before, and it's kind of a peculiar phenomena. The interesting thing about this phenomena is that, first of all, the learning rate, but by choosing different learning rate, you cannot control this oscillation. The oscillation, the amplitude might change, but the frequency of oscillation remains. And what my colleagues noticed that is actually this frequency is dependent on the gap between the ground truth value of W, the optimal value, and the quantized value. If the gap is larger, that oscillation is going to be bigger. If the gap is smaller, oscillation can be small. So something like that. The more details are in the paper. But they observed this behavior, and then what are some drawbacks of this oscillatory behavior? The first drawback is the discrepancy in batch norm statistics, meaning that the batch norm statistics that you compute during training is going to be different from what you will get at test because of this oscillation. So what you need to do, you need to recompute the batch norm statistics, which manages to solve this discrepancy issue. However, the problem is not only that. Actually, it has a negative impact on the optimization process as well. This basically means that if you look at the optimization process, this oscillation actually prevents network to converge to a better local minimum and gets better performance. So it is important to kind of overcome this oscillatory behavior.
And on that last point, the idea is that beyond just resulting in a larger error, it will prevent convergence altogether.
Or converges to a good point. So you might converge to something that is not a good place. So that is the main issue. So the other thing is that okay, what are some solutions? How you can actually deal with that issue? So my colleagues actually proposed like two methods. The first one is a kind of a dampening regularizer. The idea is when you're close to quantization threshold, you're going to see this oscillatory behavior. So what if you put a regularizer on training that pushes the weights to be close to the center of beans instead of quantization thresholds? And that already is quite helpful. The other point is the other approach that they have is about freezing the weights. What does that mean? This means if you see that the weights are oscillating, then you freeze them. You just don't update them because you know that this is going to have a negative impact. But there are subtleties in the way you do that. First of all, how do you decide if you freeze weight or not? You have to monitor the oscillatory behavior and oscillation frequency. And you basically have to compute that oscillation frequency, which they do by using some kind of exponential moving average, and then put a threshold on that. So this is.
Are you tracking this and managing this on a weight by weight basis, or are you looking at some notion of oscillation that's kind of vector based?
So as far as I know, this is weight by weight basis. Again, I encourage everyone reading the papers and all details to make sure I'm not, not destroying my colleagues' work. But I think it's a weight by weight because you compute it in a weight by weight basis. So at the end of the day, what happens there is that. You monitor that after a certain threshold, you just freeze it, and then you freeze it to a value that kind of occurred most. So there's actually like a mechanism for selecting that. As a matter of fact, with this technique, you can actually bring the quantization widths down to, let's say, 4 bits, 3 bits for, let's say, mobile net, efficient net type architectures on ImageNet data, which is a quite remarkable result.
Wow. Wow. And is oscillation, to your knowledge, has oscillation been the primary impediment to reducing the level that we're able to quantize to, or are there other key challenges there?
Yeah, I mean, I have to give a caveat that my colleagues are definitely more knowledgeable in that area, but that definitely was one of the main factors for sure. Because after fixing that oscillation problem, kind of you could do a great job that you couldn't do before. So this is definitely one important factor.
And there are another couple of papers that your colleagues are presenting.
Exactly, we can rapidly cover some of those as well. So on personalization, there is this paper of my colleagues on variational on-the-fly personalization paper. So when you deploy a model on edge device, sometimes you need kind of personalization of that model specifically to the user that is using it. Let's say, for example, let's talk about the speech verification, right? You want to be able to personalize the machine learning model that you have for a specific user that is using that service, right? Now, there are some challenges for personalization. You really don't want to do on-device training because of the kind of you don't know what's happening. You have to monitor everything, and it's kind of challenging. You want to do it in an unsupervised way, right? You want to do it few shot, so you really don't want to get that much label from the user, and you want to do it with few samples. And yeah, I mean, you don't want to basically send data back to a source, so you really want to be able to do it on device and kind of without requiring retraining and all that. So then this personalization problem was formulated using a variational principle. The idea is that you actually train a so-called variational hyper personalizer. So we call it that way. So there's this hyper personalization basically a network that gets those few samples, and basically based on that updates weights of the model according to those samples. So it's just a way of adjusting the distribution of those weights to the model that you're getting. So, of course, there are more details in the paper, but the core idea that we have there is that, this is the first time that you can do on the fly personalization. And yeah, I think it's very, very important for edge device machine learning model deployment.
Awesome. Awesome. And the last one that we wanted to cover was on kind of causal identifiability for or from temporal intervened sequences or CITRIS. What's that one about? Sounds juicy.
Indeed. That's a 40-page paper. So I also encourage everyone to go and read all the details. It's a very exciting topic. I mean, we all know that causality and identifying causal factors are quite important. So the core idea of the paper is that first you represent your causal factors as a multidimensional vector. So that's the first thing. This is representation of causal factors. The second thing is that the data that you have and based on which you try to solve this problem, this causal identification, is basically it works based on access to a temporal sequence in which there are some intervention is happening. So basically, there are some interaction with the scene. So through that, you can actually figure out some causal factors out of those interactions and out of the temporality that you have. So then there is a VAE model is proposed where the causal fact, the latent space of that are basically in the latent space of that, you can disentangle causal factors represented as these multidimensional vectors. So basically, you can, in the latent space of that VAE, you can actually disentangle causal factors using having access to those things. And the other one interesting thing about the paper is that this is just not like you can use that VAE, but as a matter of fact, if I give you an arbitrary autoencoder, right, pre-trained autoencoder without knowledge of this, then it is possible to train a normalizing flow that manages to disentangle causal factors from the latent space of that autoencoder, which is actually quite an interesting thing. So I think definitely encourage everyone to go and read the details of the paper.
Awesome. And before we finish up, we also wanted to touch on a workshop that you're participating in, your colleagues. This one on Bayesian optimization.
Yes, exactly. So that's also an interesting paper by my colleagues on Bayesian optimization for macro placement. So what is macro placement? So if you look at kind of a chip placement problem, you basically have macro units. Those are memory blocks that you have, and then you have standard cells that you can put on the chip. So usually you design you place all those objects in chip under some constraints. These constraints basically are you can say power, performance, area. Those are very important constraints. But to evaluate these for each placement that you choose, to evaluate the objective function that you have is very costly because it has to go like a lengthy simulation and kind of compute everything. So you really cannot integrate that in the optimization loop. So you have to use some sort of a black box optimization for that. And people kind of traditionally use simulated annealing type methods, but Bayesian optimization actually provides an elegant way, an alternative way of solving this problem. It's a combinatorial optimization problem. So it's a tough problem. And Bayesian optimization, roughly like you build a surrogate model and you have access to use a Gaussian process to build a surrogate model and basically integrate that, use that for your optimization. So the contribution of the paper is basically solving this macro placement problem using Bayesian optimization. Also very, very interesting work and of course, quite important for what we're doing.
Got it. And that one's at the Real ML workshop. Do you know what the Real ML acronym is?
I cannot remember,
Okay.
but it was. I think it has something to do with active learning for real world systems.
Real
something
world
like
active
that.
learning and machine learning or something like that. Yeah.
Exactly. But I cannot remember. Those are complicated names sometimes. So.
Awesome. Well, Arash, in terms of your research on kind of machine learning for wireless, what are some of the future directions that you're excited about?
Yeah, I would say I think I touched a little bit on this modeling part. The fact that channel modeling, let's say wireless channel modeling, at the end of the day, it's about learning physics. Neural networks that are integrated with this bias coming from physics, or they can learn part of physics. That's a very, very interesting and exciting research direction for me. And it's kind of as we investing a lot of time on that. I hope that in a couple of months, I can be back and talk about that. But that's a very interesting research topic, and I think it can be quite game changer.
Well, thanks so much for joining and sharing a bit about what you're up to and your work, your presentations at ICML.
Yeah, absolutely. Thanks for having me. It was a lot of fun.